Today's talks will be focused on earthquake resilience in Dharamsala. Our first speakers today will be Dichin Sogyal and Choyongla from Studio Nyandak, followed by structural engineer Paul Laroque, and we'll have a 20-minute Q&A session following these speakers, then a short break, and then we'll reconvene to hear from Marietta Garcia Nunez and Dr. Javier Ortega Jerez. Then we'll end with a Q&A session as well. It's my honor to now introduce Geshe Laktorla, the director of the Library of Tibetan Works and Archives, to say a few words of welcome before we start our talks for today.
I did my talking yesterday, so I'm here only to welcome today's speakers and all those you who are attending. His Holiness the Dalai Lama repeatedly says there are two types of suffering: man-made suffering and natural disaster. Unfortunately, many times, much of our sufferings are unnecessary suffering, which means man-created suffering. So we should really focus on not to create this unnecessary man-made suffering. And on top of that, we also have natural calamities like the earthquake and so forth. So it's of course very important for us to deal with all kind of problems, man-made, natural, whatever, because we all want happiness, do not want suffering. So they are especially, today's topic is relevant, especially here in Dharamsala. Of course, it's relevant to many, many places where there is earthquake and seismic, risk area. So it will be wonderful to listen to the today's speakers based on their own experience. How should we deal with such problems? Because many people, when they talk about, fighting against the earthquake disaster, they always think about restructuring the house and all those big things, which is true to some extent. You can do the retrofitting and so many things, but that's not everybody can do. But there are many things which we can do, like make sure that there's no fire hazard, no flood, proper medical facilities around, foods are available, and so on and so forth. So if I speak more, then they'll say, oh, Kishila, you are talking what we are supposed to talk. So somebody already complained this to me. So I'll shut up and go. Thank you. Welcome, everybody.
We begin today's session with a presentation from Dichin Sogyal and Choyongla, engineers at Studio Nyandak's Dharamsala office. Studio Nyandak is an architecture and engineering firm based in New York City and Dharamsala, led by architect and structural engineer Tenzin Nyandak. The studio is deeply committed to cultural preservation, resilient design, and community engagement, particularly within the Himalayan context. Drawing on FEMA's rapid visual screening tools and adapting it for local conditions, Studio Nyandak's Dharamsala team is currently mapping seismic vulnerabilities at Upper TCV and Delek Hospital to develop a seismic risk assessment method that can be used for critical infrastructure across Dharamsala. Supported by the Tibet Fund, Studio Nyandak is also researching design strategies for building a small-scale earthquake simulator table that the team will use for developing earthquake-resilient retrofitting designs. Today's talk will highlight both the technical findings and the broader implications for safeguarding life, property, and heritage in the Himalayan foothills.
Hello. Okay. Dastle, and greetings to all present here. Thank you very much for attending the conference. I am Dechen Sogel from Studio Nyandak. It has been 2 years since I have been working in this architecture and engineering firm. Today, I, along with my colleague Chiangla, as Yumtola mentioned, will be starting our conference with the presentation on the seismic risk assessment, especially focusing on the Dharamsala area. So before moving forward, I think it is getting repeated, but still, like, I would like to say thank you to Tibet Fund for supporting our studio, especially in building a small-scale earthquake simulation table that we are still working on and it's in progress. And then we have researching seismic risk assessment, which will be further discussed by Chiang Lao. Without further ado, let us begin. First, as you see on the slide, I will be covering the topics on the left side, and Chiang Lao will be continuing the topics on the right side. And my topics include introduction to earthquake, earthquake zoning, followed by the geological map of Dharamsala region, and then at last, I would conclude with the earthquake predictions and probabilities. So earthquake, Keshila Haktorla mentioned, right? It's one of the most deadliest natural disaster. And the earthquake, the term itself, it can be defined as the ground motion or the movement on the Earth's surface. And the ground shaking, it can be induced by various factors. For example, it can be a human-made mining accidents or activities like explosions, and also like natural volcanic eruptions can lead to ground vibrations. And then we have the Earth's surface, which consists of segments of rock layers, which is termed as the tectonic plates. These tectonic plates move with each other in a different speed and different direction. And then if you see on the diagram, there is this focus which is within the Earth's surface, and it creates a seismic wave which which outreach to the Earth's surface, and directly above that point, there is an epicenter. And the focus, it is where the seismic waves originates. Okay, wait, sorry. So just like I said, like the tectonic plates move with each other, right? And when they move with each other, they build up a stress and strain. These energies, they get stored up, and that sudden release of this energy creates these seismic waves, which we term it as earthquake in a usual life. So, and then we have scientists and geological experts who use tools like seismographs to scale and measure the seismic waves, and then it determines the intensity and the magnitude of the earthquake. Moving forward, so if you see, there is this Indian plate in the south and Eurasian plate in the north. So what happened was 50 million years ago, there was this collision between the Indian plate and the Eurasian plate. So the Indian plate moved northwards to the Eurasian plate, under thrusting into the Eurasian plate, and then created this seismic belt, a Himalayan arc. And then the Himalayan arc, as you see, is this orange line, the orange arc, and it extends from the northwest Kashmir to the northeast Arunachal Pradesh. And this continental to continental collision, it created the Great Himalaya. Himalaya is 2,500 kilometer long, and the width varies from 250 to 350 kilometer. And then due to this collision, the Indian plate, it moves continuously at a convergence rate of 40 millimeter per year. So the Indian plate is continuously moving northward to the Eurasian plate. And then obviously, like simultaneously, the Himalayan range, the mountain ranges increases in elevation every year. So, okay. This slide, it shows the major earthquakes recorded in the history that hit with a magnitude more than 7.5 in the Himalayan region. So as you see, between 1897 to 1950, there was a phase where there were a high seismic activity, and then initially in the 1897 Shillong earthquake with a 7.5 magnitude occurred, and followed by the most devastating Kangra earthquake in 1905, which hit with the 7.8 magnitude. And then it was followed with 1934 Bihar, and then the 1950 Arunachal Pradesh earthquakes. And after 1950, there was no major earthquakes observed until in 2005, the Kashmir earthquake happened with 7.6 magnitude. And then recent major earthquake was in the 2015, where the Nepal earthquake of 7.8, which is similar to the Kangra 1905 earthquake magnitude, happened. This is the earthquake hazard map that shows the seismic zoning as per the Bureau of Indian Standards. And it is overlaid with the seismic activities of magnitude more than 5. So the seismic activities, the circular dots that you see are all the seismic activities which are above the value of magnitude 5. The table on the right upper corner, those are the zoning classification according to the recorded seismic activity over the years. And then the Himalaya region, of course, as I mentioned, is the most active region when it comes to the seismic activity. And Himachal Pradesh, if you see on the northwest side, Himachal Pradesh lies in both the zone 4 and 5. So, but like around 98% of Kangra district in Himachal Pradesh itself, it lies in zone 5. So the red color you see on the Himachal Pradesh, it's where the Kangra lies. And then, therefore, we need to pay special attention to the buildings, making sure that it follows the seismic standards, design standards, and assess the existing buildings as well for earthquake resilience so as to be safe. Focusing on the Himachal Pradesh state itself, I will be talking about the major thrust and the geology of Himachal state itself. If you see, I have the MBT, main boundary thrust, MCT. These three are the major thrusts that are along the length of the Himalayan arc. And if you see the color coding, so these major thrusts divides the geological zones into 4 parts. So these 4 parts are Shivalik ranges, Lesser Himalaya, Great Himalaya, and the Tethys domain. And the Kangra, the Dharamsala area itself, it lies in the Lesser Himalaya region. So what it means is that the Lesser Himalaya region contains Takshai and Kasoli formation. In simple terms, it contains mudstones and sandstones, and the area is primarily consists of alphisols, which is a sub-mountain soil, and it is layered with shale and siltstone. So these soils are rich in clay content and overall suggesting a strong bedrock, but then a weak surface deposits of the area, and it additionally factors in amplifying the hazard risks. And here we have a slide which shows the most severe earthquakes in Himachal Pradesh recorded by the State Disaster Management. And the table shows when and where the earthquake happened, along with the magnitudes, and then the damages or the casualties it resulted in at that time. The first row shows the most devastating earthquake, one of the several devastating earthquakes that was recorded in the 20th century. 1905, 4th April, it occurred in Kangra at 7.8 magnitude, which resulted in around 20,000 people losing their life and more than 1 lakh homes getting destroyed. And then we have following rows with moderate seismic activities. But if I were to focus more on the Dharamsala area, we have the 1986 earthquake that happened with a magnitude of 5.5. And if you see the difference, so you can observe that the less magnitude it hits, the less casualties we can observe. These are the pictures taken by CS Middle Mist who came to Dharamsala after the 1905 Kangra hit. While investigating, she took those pictures, and I retrieved those pictures from her investigation book. And if you see on the left side, the old British barracks and then the church, the walls are partially collapsed. And then on the right side, the bazaar and the Meglodganj market, it is totally collapsed. So these buildings were mainly built with unburned bricks and mud blocks. And we can still find housing similar to those in the Dharamsala area, especially in the village areas, and it makes the people residing there vulnerable to the hazard. So we have this slide which shows the perspective view of Dharamsala area. Looking from a satellite imagery, Dharamsala is generally a name given to several settlements which are located above the Kangra Valley. And this area is growing rapidly in terms of population as well as construction. Of course, we all observe it and we all realize how rapid the construction and the housing are getting built. So as per the Department of Town and City Planning, they have recorded a 2011 census of total population around 92,000 total population, and then they have estimated a 2035 projection total population of over 2 lakh people, and thus increasing the amplification of hazard with more buildings getting destroyed and more people losing their lives. Hence, a controlled planning and building construction should be followed according to the seismic standards and reduce the hazard impact. This slide shows the crucial infrastructures. The red arrows are the locations of those structures or buildings. Especially a hospital, for an example, are necessary for preparedness during hazards, which may lead to more people losing their life if not made resilient when it comes to earthquake. And then according to the Indian standards, standards or codes, we also have other important buildings which include not only hospitals but schools, emergency service stations, and government offices and halls or auditoriums, and then places of gatherings. So places of gatherings are also a necessary place to be prepared. This slide shows the ridge line, the high ground line, which extends from the Doladar range in the north to the Kangra Valley floor in the south. So from Meglodganj, Baksunath in the north to Kotwali Bazar or Kacheri in the south, as you can see, the line extends. And the average elevation of Dharamsala region, it ranges from 4,000 to 6,500 feet. And if we were to show the slope on this terrain, then it looks like this. So the red arrows that you see are the slopes which are greater than 20%. And the north side of the Dharamsala area, it has a very steep slope, more than 25%. So we can see the high intensity of housing and constructed along the steep slope, which is a very triggering factor when it comes to earthquake. And steep slopes are also very prone to landslides, which occur during the slope failure in monsoon, and then most importantly, post-high intensity earthquake hazard. So thus the construction in the steep slope, of course, is not recommended. Lastly, I would like to conclude my presentation with this slide, which includes the recurrence probability of earthquake in the Dharamsala area. And as you can see on the top table, there were geological studies and seismic analysis done by geological experts and researchers. And one of them are Nicholas and Roger, who have estimated that more than 7.5 magnitude of earthquake will occur in the time interval of between 50 to 200 years. And then we also have Mridula from IIT Turkey. Her research says that more or equal to 8 magnitude earthquake will happen during the time interval of 2003 to 2109. So it shows an earthquake possibility as severe as the 1905 Kangra earthquake in the next 50 to 100 years, approximately. And then at the bottom, we have the hypothetical earthquake estimation. This estimation is done by a former national seismic advisor, Professor A.S. Arya. He estimated that if an earthquake similar to 1905 Kangra earthquake were to happen in the year 1991, then the casualties, as you can see, for the non-engineered buildings, the scenario when the earthquake hits in the winter midnight will lead to around 65,000 people losing their life, and half the number if it occurs in the daytime. So, but if you see, on the other hand, if the buildings are engineered buildings, then the casualties and the people losing their lives reduces to approximately 12,000. That shows a big difference between engineered buildings and non-engineered buildings. So the question of Kangra type earthquake is highly debated because even the geologists cannot tell when it will occur. But then, however, it is on us to be prepared and to be aware, and sustainable development shall be practiced to avoid the damages they leave behind. So let us be alert. This is the end of my presentation. Thank you for listening. I will be followed by Shangla. Thank you.
Thank you, Dechen. We can now explore about how rapid visual screening and risk management can integrating them into will help with our community's earthquake preparedness. So this is particularly crucial to Dharamsala, our region, given its high seismicity and building vulnerabilities. So in my presentation, I will cover from risk management strategies to rapid visual screening and assessment methods as well. So these two terms that you see on the screen are earthquake hazard and earthquake risk. So these two terms are often misunderstood as the same thing. But earthquake hazard and earthquake risk have actually different meanings. So earthquake hazard talks about the records of earthquakes, data on the geological setting of the region, and the ground shaking models of the region, whereas earthquake risk actually factors in the earthquake hazard into the data, with the local soil conditions and the area of exposure of the region, and the building weakness of buildings. So to put in simple terms, earthquake hazard is actually the prediction of earthquake based on past data, whereas earthquake risk talks about the potential damage of such earthquake for the region. So hence, information regarding the earthquake hazard is a prerequisite to defining earthquake risk, and that's what Dechen just explained to us all, the earthquake hazard of the Dharamsala region, so that we have a better understanding of such earthquakes in this region. So, and understanding this hazard level is the first step in effective risk management. And let us now discuss about the risk of earthquake, I'm guessing as everyone already knows. So when an earthquake strikes, there's actually two major effects, so the primary and the secondary effects. So the primary effects are those direct effects as a result of the ground shaking. And the secondary effects are the consequences of those primary effects. So, and if I were to talk about the risk, so in the photo, as you can see, we have the primary risk. So ground shaking is the most common and widespread effect causing structural damage through seismic waves. So damages from buildings, infrastructure, roads, bridges, everything. So which makes it harder for rescue operations, recovery, and connection between places. So the photo on the left, as you can see, is of the Bhuj earthquake in Gujarat, India, in the year 2001. A 7.6 magnitude earthquake struck the region, resulting in a loss of over 20,000 lives and an economic loss of about 22,000 crore rupees, or approximately $5 billion. And the photo on the bottom right that you see is of a ground rupture. This was of a small earthquake, 4.3 magnitude in Chamba in the year 2016. right? And ground ruptures are actually is when the surface breaks along the fault line, which can cause critical damage to the fault lines, where the fault lines are, right? So it directly impacts the structure, anything above where the fault lines are. And even though the magnitude was small, you can see the damage, the significant damage it has done to the roads. And what's important out of all the risks is the loss of lives. So buildings, infrastructure, roads can be repaired, but loss of, I mean, these can be repaired, but loss of lives are irreparable, as we all know. And so there are other primary risks other than these, but are of lesser concern to the region, such as tsunami and liquefaction, because we're up in the Himalayas, so it's not so much of a tsunami concern. Right? So the consequences of the primary risk that I just covered leads to these secondary effects or risk, as we call it. So landslides. So Dharamsala, as we all know, we live in a mountainous terrain. So our mountainous terrain is we're particularly vulnerable to earthquake-induced landslides. So the photo you see on the right is of Shimla in 2024. Yeah. And so the constructions done without proper geotech survey or proper engineered design can actually lead to premature landslides, as you can see in the photo right there. And socioeconomic impact. So earthquakes disrupt livelihoods, tourism, and local economy, which can lead to displacement, loss of information, and loss of actually cultural, authentic cultural information. So for example, the Library of Tibetan Work and Archives that we're currently in actually has a lot of important Buddhist texts, right? So back in 2006, as Keshil Haktola mentioned yesterday, Geohazard International, a non-profit working towards global earthquake safety, came and visited the site with a lot of US engineers. And they recommended that a lot of the books and shelves in the library building were not properly secured. So that could actually lead to the loss of such texts, right? So if there was an earthquake, even though the building is safe, the books and shelves could fall down and the text could get damaged or lost. And to talk about fires, so secondary fires from earthquakes is actually more devastating than the earthquake itself. So the photo you see on the top right is of the 1994 earthquake in California, US. So the fire that you can see in the photo is actually from a gas main which was caught behind a crater that caught fire and resulted in a lot of houses being burnt in that region. And flooding is also a risk, which is not shown in the photo. It's also a risk which is quite doubtful in this region because we're up in the mountain or the hills as we call it. But it could actually lead to flash floods and rivers could change. The courses of the rivers could change. It could affect smaller regions, right? So therefore, effective planning must address these impacts, and a quick and convenient way to mitigate the seismic risk is to assess the buildings that we live in through rapid visual screening, right? So RVS, or rapid visual screening as we call it, is a practical first step in seismic vulnerability assessment. So RVS is a method for quickly evaluating the potential seismic risk of a building by noting the key structural and non-structural elements of a building. And so building construction type is one of the key factors. It's a foundation for vulnerability scoring. And earthquake zones and soil conditions also significantly impact the vulnerability. So if you were to look in the middle of the screen, where there's a bunch of numbers and tables, so the first table is basically, the first row is basically the building topology. So based on the building topology, you get a basic score given, whether it's a reinforced concrete or a wooden structure, you get a score given. And then you have score modifiers below with a bunch of numbers where you can see. So those score modifiers are then factored in building based on the building parameters. And then an overall score is given. So based on the overall score that the building receives, by subtracting from the cutoffs from the modifiers, if the building is below the cutoff score, the building is deemed unsafe and will require further screening or testing. And other than this, there are like other analytical methods to assess the building for seismic vulnerability, but they require more resources and time. So hence the name rapid visual screening, which is very quick and convenient. And the FEMA P154 form was one of the first forms developed by US in the 1980s, and the form has evolved into this form. This is like, I think, the third iteration of this form. And we have other rapid assessment methods in addition to the one developed by FEMA that you just saw earlier. So here are some examples. So this one particularly is developed by UNDP, and it's actually developed for developing countries. and it's designed to work with like limited technical expertise and resources. So this one is actually developed in India by NDMA, National Disaster Management Authority, and this one is actually developed in India, so it has been developed using Indian specific guidelines. And so this form here, this is interesting form. So this is uh, developed by Taru. Taru is a consultancy firm. So they made this form in collaboration with Himachal Pradesh State Disaster Management, and they actually developed this form for the Indian Himalayan region, where the building infrastructure and communities are very vulnerable to earthquakes. So based on those specific parameters, they developed this form. So all the forms that we saw prior to this, the previous four forms, all have the same purpose in assessing the buildings. So rapid visual screening, that's the key purpose. And what they vary in is the grading system. Some have scores, some have grading, so that's how it varies, but they all have the same purpose. Right. So this is from one of our case studies, and that was upper TCV, which Yumso covered earlier. So this form actually shows a completed assessment form, and it actually demonstrates how various building parameters are systematically evaluated, as you can see in the table. So each information is given about the building, and as you can see the odd shape of the building, so each comment is mentioned in, because the RVS is a very quick way to assess a building. So you don't get a lot of boxes to tick, but then you can add comments about the various parameters of the building, right? And each section actually captures the critical structural and non-structural attributes of the elements of the building, whether be it if it's a plan irregularity or vertical. And then the scoring system, as you can see on the table with the numbers, you can see small boxes, small circles. So that's the scoring system with the score modifiers, and then overall score of 0 is given, right? So that's actually below the cutoff, which deems the building quite unsafe. So ultimately, this RVS method forms the basis for prioritizing whether it should be retrofitted or it should be replaced or rebuilt based on the building parameters, right? Okay. All right. So upper TCV case study. So this is a case study we did for RVS. So as continuation to one of our pro projects as part of Studio Nyanda, we were able, the rest of the team were able to conduct RVS on various building blocks of TCV, as you can see on the color-coded map. So this research work aided by Tibet Fund's grant, our team visited TCV school and conducted RVS on all the various building blocks, right, as I said, and actually converted the data into an Excel spreadsheet. But to visualize the data, we actually made a photo map, so it helps us to better understand the priority level of each buildings. And what's also interesting is all of us doing that team in India and Yandala are all members of TCV. And as I'm pretty sure, I think most of us would know, the motto of the school is come, come to learn, go to serve. So we all feel pretty grateful that we were able to contribute to the school in this manner. And so I'll talk a bit about Upper TCV school. So this is just a small region of Upper TCV. So the Upper TCV school actually covers an area of about 40 to 43 acres roughly. And the school houses about 1,200 students and staff, and it comprises of various buildings from classrooms to boarding houses to residential units to office and auditoriums and everything. And the school is actually located on a ridgeline, and majority of the building blocks are built onto a slopey terrain. So the two photo maps that you see on the screen are of the building usage and construction type. So in building usage, the photo on the left, you can see it's color coded. So it shows from the blues are from utility, whether be it auditorium, staff center. The greens are residential, and the lighter greens are actually the office and the classroom units. And in construction type, TCV is, even though it was built in the 60s, as time progressed, even the construction topology also changed. So TCV, the blue ones are actually unreinforced masonry load-bearing structures. So TCV primarily has reinforced concrete structures, but what's interesting is that most of the reinforced concrete structures in TCV predate seismic codes, or they were built by local masons. So they didn't really have like an engineered design to it. Right? And okay, so okay, that was two parameters that I just talked about earlier. So these two parameters are actually quite important in terms of the RVS form, and that is the plan and vertical irregularities. So plan irregularity, the photo on the left, are of those buildings. Are those buildings that have like an asymmetric layout, where the buildings, and actually like those buildings that have a plan irregularity react different to an earthquake in terms of an earthquake. This is mainly because of the ratio between the length and width. I mean, the x to y when you think about it, because the shape of the building is if it's narrow, it reacts differently to earthquakes. So if I were to put it like the allowable ratio for a length to width is ideally kept to 1:2, 1:3. So mainly if it's 10, it can be 20 or 30. But if it goes more than that, it becomes too narrow and becomes problematic for the building when it reacts to an earthquake, right? And in terms of vertical irregularity, the photo on the right that you can see is of is the photo map you can see. I mean, it shows the severity from red to white, right? So depends on when you build a building, the building should ideally be built in plane, like so each floor is stacked on top of each other. It should not be out of plan, like if one's here, it can't go way too much out, and split levels as well. And given the terrain constraints, most of the TCV building blocks were actually built on a split slopey terrain. So if a building's here, then the building goes, the above floor goes further back. So that's also problematic in a way. And so one good example that we have of vertical irregularity is the library annex halls extension block, right? So that if you look at the building from the side, there's actually a vertical offset. So during an earthquake, the building may, I mean, move in an undesirable way, which may result in twisting because there's a vertical offset if you look at the side from one perspective, right? So both these irregularities actually significantly impact the vulnerability of earthquakes, right? Of the I'm sorry, of the buildings, and this majorly like I would not say, but like this is somewhat also due to the terrain constraints that we have, and the site limitations. If I go, so this big map that you see on the screen is actually of the final risk score that we did, like the from when you do the overall RVS, when you get a completed score. So we made this form so darker the color, it means the more unsafe the building is. Greener means it's safer. So basically the lower the score, the more unsafe the building is. Higher the score, the safer the building is, right? So we have color coded the map to prioritize the vulnerability ranking. So as you can see, few building blocks in TCB school are quite red and some are green. So this result actually helps us by guiding us where the resource should be allocated and which building should be prioritized for retrofitting. So yeah, this is an Excel from our website. This is the Excel spreadsheet that we were able to make from the RVS screening. So something special that we did, additional what we did to the RVS was to factor in the human hours. So the red box that you see on the screen is the amount of human hours spent in each individual buildings. So what Yumso and I, when we were in TCB, we actually calculated the amount of human hours spent in each building block and in respect to other building blocks. And what we actually found out was that the classroom buildings and the homes actually had more human hours. As you can see, the ones with the higher blue levels, actually, those were, so that how this helped us prioritize which buildings were more important in terms of the human hours. And so this RVS method that we just talked about is actually a way to mitigate seismic risk. And other than RVS, there are other strategies that we can do. Right? So let's talk about some of them. So as we all know, Dharamsala, so Dechen just explained to us all, Dharamsala falls in a very seismic heavy intensive zone, and it is actually not a matter of if, but rather when like a heavy earthquake might occur. So it's upon us to be responsible and to be prepared for an earthquake. So these are two different terms, though closely related. So if I talk about community preparedness, the key role lies in community participation for everyone involved, whether it be businesses, individuals, residents, everyone has to be personally involved in this and has to participate. And secondly, as you can see in the photo, they are possibly discussing the evacuation procedures in terms of in an event of an earthquake or a fire. So in terms of evacuation procedures, everyone should be well informed and aware of where to go, the assembly points, where the clear routes are. And let's say for an example, if there is an unstabilized wall or a retaining wall in a building in a residential area, so people should be well aware and informed to stay clear of such areas. So this is part of community preparedness. And what's also interesting in community preparedness and disaster risk management is policy integration. So incorporating seismic safety into local building standards and codes could actually potentially save our future by building safer houses when you build it with seismic codes. So in terms of disaster risk management, we can have awareness campaigns as you can see in the photo, and we have early warning systems set up at different locations around the town, and we have emergency response ready to go when it's needed, and then resource mobilization to keep certain resources available at different places, vantage points, I'd say, and recovery planning that we can like post and disaster, we can actually have guidelines already set up pre-hand, so we are better able to handle the situation if an earthquake does occur. So that was about what we as a community can do to stay prepared for an earthquake. But in terms of the buildings that we live in, there are different ways to strengthen our buildings and to reduce the damage from the results of an earthquake. So in terms of reinforced concrete structure, the photo on the left is a photo of column jacketing. So that can be done to reinforce to strengthen an existing reinforced concrete structure. And the middle photo is of unreinforced masonry structure. So this technology, as it states there, containment reinforcement technology, was actually developed by UNDP back in 2015 after the Nepal earthquake. This technology, containment reinforcement technology, has actually proven quite effective because after the Nepal earthquake, there was several aftershocks, and this containment reinforcement technology actually ended up saving a lot of buildings, which were actually quite vulnerable to earthquakes. And in terms of composite structures, this photo is actually of a soft story, and I'm guessing everyone around town might have seen a lot of soft stories, but are actually not aware what a soft story is. So soft story is actually a building block where the ground floor is, which has columns, a reinforced concrete structure has columns, but it's left unwalled, majorly for parking purposes or this big glass door fronts. So this is actually quite fatal during an earthquake. When an earthquake does shake, the ground floor, the top of the ground floor column, when you look at it, shifts. The stiffness is very stiff, so it could react in a very undesirable way, so which could prove quite fatal. So strengthening, like this is just an example. This was done in the U.S., but this is just an example of soft story how it's quite vulnerable to earthquakes. And and also we as a firm, we also encourage retrofitting instead of rebuilding, as Keshila suggested, because there's less environmental impact and it's cost saving. And as an architect, there's an architect in the US, as he said once, the greenest building is one that's already been built. So yeah, it's better to retrofit than to rebuild if it doesn't need rebuilding, right? And to end my presentation, I would just like to give you some key takeaways from what Detso and Dechinla and I discussed. So Dharamsala is high seismic risk. So Dharamsala falls in seismic zone 4 and 5 of Indian code, and which actually requires proactive measures in terms of building infrastructure and vulnerable infrastructure. So majority of the building blocks around Dharamsala predate seismic codes. So most of the buildings are built without proper engineering, so which is very vulnerable to earthquakes. And tourism dependency. I think the name itself is self-explanatory, and because Dharamsala has a lot of tourists coming every year, so economic resilience depends on maintaining safer and functional infrastructure and community preparedness. And as I mentioned earlier, we as a community all need to be involved to be better prepared for such events. And before I end this slide, I would like to reiterate the photo as you can all see on the slide. So earthquakes actually don't kill people, so buildings do. And so it's upon us to be better prepared and yeah, to be aware of such situations. Thank you.
Our next speaker today will be Paul LaRoque, a structural engineer whose work bridges cutting-edge design and deep historical understanding. With degrees from MIT and the École Spéciale de Travaux Publics in Paris, Paul has a wealth of experience in structural engineering, from rammed earth and timber to concrete and steel high-rises. He teaches engineering at both Pratt Institute and Columbia University and is a regular collaborator with Studio Nyandak's work in Dharamsala and New York City. In today's presentation, Paul will focus on reinforced concrete construction in earthquake-prone areas, particularly the prevalent structural typology in Dharamsala, concrete frames with masonry infill. He will unpack the principles of earthquake engineering, highlight failure modes observed in past earthquakes, and propose best practices for structural design and construction.
Hi, everyone. One second.
Okay.
I'm very excited to be here. Thanks, Studio Nyandak, for the opportunity and the invitation. I had a bit of a struggle to prepare this presentation because I think we all have very different background in the crowd, and my work tends to be quite technical. So I don't want to dive too deep in the pool of modern seismic design, which can be very technical. And so hopefully this lecture will give you a general introduction to what you need to know if you were interested in designing your own home and understanding better what the best practices are now. And if you see a construction site, understand what is appropriate or not appropriate for structural safety in a seismic context. So before I start, I'm going to tell you a little bit about myself really briefly. My name is Paul. I grew up in Paris, but since 2007, I now live in New York City in the US, which is where I met Tenzin. Besides working as a structural engineer, I also teach, which was mentioned previously. And when I'm not working, I really like to be outside, hiking and rock climbing, my main pastimes. I really wanted to be an architect growing up, but I really enjoyed sciences and math especially, and so that naturally pulled me towards engineering. And I'm really thankful I got there. It allowed me to work on many more projects than I would have if I had been an architect. And over the last 18 years, I got really lucky to work on a lot of projects at very different scales and with a lot of different materials, which is very rewarding as an engineer because you're always challenged with new things. I've worked on rammed earth building, bamboo structures, steel. Today we'll talk about concrete mostly, but if you have questions about other materials, feel free to jump in. A couple pictures of past projects. I'm not going to go too deep into this, but on the far top left, you see a tall concrete tower in the Middle East, which was early in my career. Not seismic, but wind controlled. Bottom left is a steel building with complex geometry. A lot of my work is based in New York City. Well, on the top right, we see an adaptive reuse of the Domino Sugar Refinery, which used to be a big factory and now is an office building with unreinforced masonry. Or a hanging tree sculpture, which is something I really enjoy working with artists with lots of different tree species that are combined together in one big hanging tree. So we'll start with a bit of a refresher on structural engineering. Then we'll expand a little bit on how seismic loads actually work. We had a great introduction on seismic risk. And then we'll dive into concrete. And then finally, we'll explore a little bit what all of that means specifically for Dharamsala and how things are built locally. So how do buildings work? We all know what buildings are for. We are in a building right now. We don't want rain on us. We want the weather to be sheltered from our lives. How does that work? How do buildings stand up? Well, in this little diagram, we see there's a lot of environmental things that can affect a building. The bottom line is that something like rain has a mass, a weight that will have an impact on the roof panels. These roof panels will in turn load the roof trusses. In turn, those will load the walls and so on and so forth until foundation, which is where the load escapes the building. And what happens, we think that the weight of the rain is no longer an issue for our building. That load path, this chain of event that happens that I just described, is critical to the structural integrity of the building. And that's the role of the structural engineer, to understand that all of the elements that are involved with the load path and the connections between these elements are structurally sound. And so there's no weak link in that load path. Obviously, rain is very lightweight and rarely a problem, but that's the same logic for any loads that may or may not impact the building throughout the life of the building. And so one of the key effort is to understand what loads are actually going to impact the building. And that's a bit of a game of guessing or predicting the future to understand what could happen. So we organize these in two main categories. We got vertical loads that are going to be gravity governed. And then we have lateral loads, which is where our big topic of the day, seismic, is going to occur. So dead loads, very common everywhere. That's just a self-weight of materials. This is a building, Dharamsala. You see concrete frame, brick infill. The weight of all of these things has a tremendous impact on the integrity. And the building is already working pretty hard to just support itself. And comparatively, if you walk in a room, the building can handle that pretty easily because proportionally your weight is very small compared to the weight of the building. Your weight is part of the live load category, which is any load in the building that can change over time. Structural engineers will design for specific amounts of people in specific rooms. So in this space, this is probably a gathering space, which would be somewhere in the middle of this picture here. But you could have lots of different kinds of live loads, snow loads, it can be quite extreme depending on the climate. And obviously that would have a pretty big impact on the design of your roof. Lateral loads are a very different animal. A very common one is going to be wind. This is the Eiffel Tower in Paris, which you may be familiar with. This building was built as a temporary structure, and 100% of the design was about wind resistance. It was the tallest structure at the time, and we can learn a lot from just looking at that. We want the building to be as narrow as possible. At the top, this is where the wind is the strongest, and so we minimize the pressure or the impact of the wind up there. We put holes inside the structure, so there's holes in the arch and in between all of the structural elements of the trusses. That allows the wind to flow through, which also minimizes the impact of the wind. And then finally, we have a really wide base, which gives us stability, which is very important to lateral forces. Typically, in buildings that are not the Eiffel Tower, we have three main categories of lateral systems. They're depicted here briefly. I'm not going to go too much into details, but typically you have walls or shear walls, brace frames which are going to rely on a triangulation for stability, or rigid frames, which is what we'll talk about more in depth later. And this is what the lateral system of this building that we're in relies on, which is the stiffness of the joints. All these systems, ultimately, their job is to take these lateral forces and then carry them all the way down to the ground, where they're going to be dissipated into the soil. So if we take a little example here, just to recap, this truck, just like a building, is seeing a lot of live load. All of these rice bags on the back are loading the truck. Those are loading the deck of the truck. That load gets carried through the axle, the wheels, the tires, and all of that gets now dumped onto the street. And that's where the foundations of the truck are located. The truck is also loaded by wind pressures when it's driving on the street or if there's side wind, and that would also contribute to a different load path. If we were to add one more bag, it's possible that maybe the truck would not survive. And so let's say the axle would break. And so that's where design really takes place, is understanding the size of this axle and the material that the axle is made of. And maybe we could use a stronger material, which is a whole other aspect of the profession. So loads is one thing, and then material science is another. We want to make sure that our elements inside our buildings are made with the right materials and have the right strength. There's lots of properties there. Materials can be very simple to use, like steel is a material that engineers like a lot because it will be just as strong in compression and tension and in shear. Other materials will be a lot more complex, and each is pretty unique. Wood and concrete, for instance, will behave differently depending on how you pull or push at them. Concrete is very weak in tension, but very good in compression. And one thing I'm going to try to introduce today is the concept of ductile materials. So each material has a bit of a fingerprint, if you will, that engineers will represent as a stress-strain diagram. And so that's a relationship between how much load we can put on a piece of material and how much that material is going to deform. And so a classic visual experiment is just to take a spring. We can pull on a spring and then we can relax the spring, and I can have the spring go back and forth to the exact same shape. And that's what we call the elastic range, and that's what we see on the left side here. And a ductile material will do something very unique, is that once it starts to fail, it doesn't break. It keeps deforming for a long time before it actually breaks. And so that's a signature of steel, which is why we use that material so much in contemporary construction. And why is it so important that a material becomes ductile? Is that it allows it to release energy without breaking. So in an earthquake event, we want things to deform and move without sudden failure, and that's what steel can do. Concrete does not do that, and that's why when we're going to talk about reinforced concrete, the reinforcement is the key player in the equation. Another good thing about ductile things, even without earthquakes, is that if we think about this beam that we have above the stage here, if this was seeing a lot more load on top of it, it would start to deform a lot before it breaks. And that ductility is what would give it deformation. And that would inform us that something wrong is going on, and we would have time to leave the building, or we would have time to repair or react to this concern. If this was not a ductile material, if it was a brittle material, that's the blue line here on the screen, then that element would break suddenly and it would collapse without giving us any notice. So we talked briefly about materials reacting differently in different directions. For some of them, fundamentally, structural engineers will think in 5 different forces and stresses. I'm not going to go too deep into these, but we have compression, tension, bending, torsion, shear. I'm happy to introduce more of those later if you're interested. We'll talk a little bit more about compression and bending because they're relevant to reinforced concrete. This is just a classic example. We all know about compression. I have a bottle. If I push on it at both ends, that bottle is feeling compression. And if I push hard enough, it will fail. And that would be a compressive failure. I could make the bottle wider or stronger if it was full, and then it would become stronger and it would take more load to crush it. A bending force is something a little bit more complex, and it's a force times a distance. Here we have a seesaw with a son and a father hanging out at the playground. The father is heavier than the son, and so to find equilibrium around the point of rotation of the seesaw, they need to be located at different locations. This is a really good illustration of what bending is, bending moment. And that would be the weight of the father times the distance of the father to the center of rotation. That would be the moment on the left side. And to find equilibrium, we want that moment to be the same as the one on the right side, which would be the weight of the child times the distance of the child to that center of rotation. So a larger force times a smaller distance is the same as a smaller force times a larger distance. At the end of the day, it's the same moment. So once we have these forces, and that's an exercise that can be quite complex to take all these loads on our buildings down into our structural elements. We essentially want to confirm that the design load is going to be smaller than what the material are able to take, which will typically quantify as a stress. Or here we have load versus strength. In this diagram, we can see that these are expressed as probability or bell curves. And that's just because loads are never perfectly known and material strength is never perfectly known. We like to think as, a piece of wood as being the same strength always, but every element is slightly unique. And so we'll work with safety factors to help mitigate these issues. And then finally, the last topic that we'll present is serviceability, which is movement. And this is something that can be very easy to see when we push on a plank. We can see that plank deforming. On the left here, I have a plank on the flat side or a plank on the vertical side. For the same load or the same length, they will deform very differently, and that's something that you all intuitively know. If you played with a ruler, you know that one direction is strong and one is weak. And forces travel through things through deformation. So sometimes we don't see deformation, but there's always some deformation. And in fact, everything is, vibrating, and that's how the rain on the roof is traveling all the way to the foundation, is through very infinitesimally small movements. So structural softwares will help us quantify all of these things. But what's really fun in the profession, for me at least, is for a given amount of material, so here we have one plank, it's going to cost the same amount to have it flat or vertical, and it will perform very differently depending on the circumstances. And so it's finding what is the best approach for the layout of the material, the shape of the material, to make things the safest it can be. So now we've all graduated from Structure 101. We're going to dive a little deeper into what seismic loads actually are. We had a really great introduction about seismic risk and how seismic loads come. Now we're going to see how these things actually travel into our buildings. So we know that in this region, this is earthquake factory. We're going to make a lot of earthquakes. And we know earthquakes travel in the ground as waves. So that's a type of load that I haven't talked about too much, but they're going to be dynamic loads. And they're going to be very specific in that regard, and I'm going to get into that a little bit more. They travel in all sorts of directions in the ground from the epicenter. And we saw earlier that the closer you are to the epicenter, usually the worse it is in terms of energy transfer. Obviously, when an earthquake happens, there's tremendous amounts of energy, especially compared to the scale of a building or a human. But what's also interesting to highlight is that the geology of the ground will also affect how these energy waves will travel. And so you might be pretty far from the earthquake and still see a lot of energy from it because the ground structure is really good at transmitting energy, or you could be in another spot where the ground is really good at dissipating energy closer to the earthquake epicenter. The bottom line is that the earthquake travels as a wave, and that is an acceleration related to time. So at usually the beginning of that energy release, you'll have a lot of energy traveling, and that's what we see here as a lot of acceleration. And then over time, that energy kind of dissipates, and that's what we see in this signature. So every earthquake has its own little signature like that. And here we see that the signature frequency for that earthquake, which is the 1991 Utakashi earthquake, was about 4 hertz, right? This is kind of an arbitrary number. That means for every 1 second, there's going to be 4 vibrations of energy traveling through. And we'll see that that matters quite a bit because the building, we talked about the earth moving, but the building is sitting on the earth. How does that really affect the building? Really, what we talk about when we talk about seismic loads, we talk about inertia. And the heavier the building, the more inertia it has. And that inertia is the relative movement of the building with respect to the ground. So the ground is moving, and then the building is like, oh, the ground is moving, I need to move now. And by the time the top of the building realizes the ground has moved, it's trying to catch up, right? And there is a differential between how the ground is moving and how the building is moving. And that differential of movement is what's generating loads inside the building. And so the stiffness of the building will matter a lot as to how much of that discrepancy there is between the ground and the top of the floor, the top of the building. So in an ideal world, we could isolate our buildings from the ground. And this is actually a technique called base isolation. This was theoretical for a long time, but we've implemented this in a number of buildings in California and Japan, where we put our buildings on wheels. And if the earthquake moves, the ground is moving a lot, but then the building doesn't really care because it's just on its wheels and the wheels are spinning. So in this idea, the building is not seeing any earthquake loads. So a little video that I think is really helpful to understand the complexity of this topic and how the frequency of the ground shake may or may not affect your buildings depending on the stiffness of the building itself. And so this is something that we call natural frequency. Each building has its signature natural frequency. The same way that you have a natural frequency as a pendulum. So if you're a little kid on a swing and you push a little kid on a swing, you don't need a lot of energy, right? You just need to time very well when you push the kid, right? You can push a very little and just time it just right. And if you push your child at the exact right moment, you can send your child all the way around the swing. That is what happens when you hit the exact frequency of that system, which is the child on the swing. Here we see that we have a shake table, and we're shaking the table at very specific frequencies. And depending on the natural frequency of the sample, so we have 3 buildings that are represented here, we see that only one of the samples is affected by the given frequency of the shake table. And so this gives you a really good sense, I think, that for a very specific natural frequency of an earthquake, there is going to be a really bad frequency of the building that would be very detrimental, and other frequencies that would be better. And the way the world works, taller buildings will be much softer, and they'll be controlled by wind. And short building will have much higher frequencies and will be much more sensitive to earthquake, which is very unfortunate for us because we build lower rise buildings and we live in a seismic zone. So to summarize our seismic loads, obviously it's about ground motion. We can do very little to control that. That's just a given. What we can do is control the mass of the structure. We see that the heavier the building, the worse it will be in terms of performance in a seismic event. And then we can also control the stiffness of the structure. If it's a softer building that will be able to move more easily, then it will attract less seismic loads. Now let's talk a little bit about concrete. Concrete, you probably know, was invented by the Romans a long time ago. The Romans disappeared. They left us one of my favorite buildings in the world, the Pantheon. The technology was gone for a long time until it was discovered again 1800 years later. But basically it's a liquid stone, right? That's going to solidify after it's set and will strengthen over time. The magical ingredient in concrete is going to be Portland cement. The Romans were using pozzolan, which came from a volcano. Portland cement is just a man-made version of that. And to make concrete, you mix water, cement, aggregate, sand, and you get a cake batter that will harden over time. And depending on how much cement and water you put in the mix, you'll have different strength. And this is a bit of a hot topic in the region, is quality control of the actual concrete. A lot of people will say concrete mixing is more of an art than a science. And a lot of people will compare that to baking. You really need to follow the recipe. But the bottom line is that contractors will often cut corners and you'll have a concrete that will be weaker than it should be, which obviously is bad. So we talked a little bit about bending earlier. I'll attempt to go a little deeper. But we have an example of a beam here at the top with a load in the middle. And what we see is that we have cracks that are forming at the bottom. And this is the idea that when we push on that beam, it will deform. And that deformation will generate tension on the bottom face. And that's why these cracks would be generated if this was plain concrete. On the bottom right, you cannot see this idea that as the beam deforms, The top of the beam here gets squashed, which represents compression, and the bottom of the beam gets stretched, which represents tension. And I mentioned earlier that concrete is really bad in tension, and so that's why the cracks form, because it's getting pulled and it doesn't like that. And that's the whole magic of reinforced concrete, is to prevent these cracks from opening. We'll just provide steel inside of the concrete, thus keeping the cracks closed and allowing the system to resist the load. The beauty of that approach, which was invented by Gardner from France, is that the concrete will protect the reinforcement from fire and water, and reinforcement is very sensitive to that. And then the reinforcement will help the concrete survive some of these loads. So it's a very symbiotic relationship. Here we have examples of reinforcement in the field before the concrete is poured. If you walk around Dharamsala, you see a lot of reinforcement sticking out of walls and columns or in construction sites. But generally speaking, we don't really see reinforcement. And that can be a big challenge with concrete construction, is that we don't really know what was installed. And there are some very sad, unfortunate stories of contractors that will install reinforcement. Someone will go and inspect, make sure everything is right, and then they'll take the reinforcement away and pour concrete to save money, because the steel of the reinforcement can be quite expensive. But that stage where you check that reinforcement is in the right place is a key aspect of reinforced concrete construction. Concrete detailing, I'm going to talk about that a little bit. I'm going to try not to be too technical, but it's really at the heart of good reinforced concrete practices. And it's a very misunderstood aspect of the work. There's lots of kinds of rebar, which is the name we give to reinforcement, or steel bars inside concrete. Here we see rebars that are going to be specifically implemented to resist shear loads. Shear is when things try to break along vertical lines or horizontal lines. In columns, we'll also have very specific patterns for reinforcement to resist these compression loads or buckling loads. And then the rebar is obviously a really key aspect of the whole process. We want to make sure the tension that can travel from rebar to rebar throughout the structure. And that can be quite tricky. And that happens through the texture of the rebar and the contact with the concrete. And lap splice essentially is the key thing here to remember, is that you're not going to have rebar that's infinitely long. And so you always need to splice things over and have an overlap that will allow the tension to travel from one end to the other. The larger the force, or the larger the rebar, the longer your lap splice needs to be. And sometimes these lengths needs to be quite significant, which is a big issue for contractors because they don't necessarily calculate the cost of this lap splice, which is twice the reinforcement. Anchoring into concrete is also a big issue, and making sure that your rebars are properly set inside, so when you pull on them, they don't come out. Now let's talk a little bit more about the specific systems that we see in Dharamsala and in the region and beyond, which is what you kind of see illustrated on the right here. It's a slab, which is kind of a flat extrusion of concrete on which we're going to walk. And that is supported by beams, which are these linear elements that connect the columns. And that's one panel, right? Typically a building will have a number of these repeated in plan, left to right. All of these in Dharamsala are, to my knowledge, founded on shallow foundations, which will be typically spread footings. And it's essentially like feet, right? Our feet allow to spread our weight onto the ground. And if we, walk on snow in the winter, we want rackets to distribute our weight so we don't sink into the snow. The more load we have, the more we want our footings to be large. And then the key player here is this lateral system element line at the bottom here, is how is this system resisting forces coming from the right. So if the wind is pushing here on this building, or if an earthquake happens, how does this building not tip over? Or how does the columns not break? These columns are the only structural element that connects the building to the ground. So we know that the lateral forces have to travel through there. This is a very typical vernacular here. We have our concrete frame. We see the columns, we see the beams, we see the slabs. With these slight overhangs, those are very simple to achieve. And then we see our panel infill, which is brick typically, which is very affordable and is typically considered non-structural, though obviously the weight of that facade is very significant. So how do these columns and beams resist the lateral forces? This is what we call a moment frame. And if you had a bunch of sticks and tried to build a little frame, which I'm sure you've done as a child playing around, you would know that this would instantly fall down because this is not stable. And the one way to make this, to create stiffness, is to reinforce these joints. And so that's what the moment frame is about. It's going to carry this lateral force through moments, which is something we talked about a little bit. And those moments are what allows this system to be stable. And the key here is that we have a lot of extra forces in the beams and the columns just from that lateral force. So on the way here, we took this picture. This is a building under construction. You see here an elevation with a moment frame. We got 3 floors. The force would come at each floor from the earthquake load. That's the inertia and that's the weight of the floor itself. And that gets carried through the columns in bending to the ground. And at the base, we would have lateral forces from each column, and then we would have an overturning effort at each base. So that's the vernacular. How do we prevent buildings from falling down? And how do we try to improve the quality of our built environment so that things are safer? This is a picture from a building in Myanmar after the earthquake of 2025. You see a building that is mostly intact from what we can see, except for the lower levels, which have collapsed, which is a very typical striking picture. This is a less fortunate example where the entire building is completely collapsed, but the floors you can see are mostly intact, right? The columns are the weak link. And that's a pretty systematic issue with concrete reinforced moment systems. So minimizing the risk can come from lots of angle, and I think we saw a little bit of that in the previous presentation. Some of it is much harder to control. Soil, faulting, like these things, basically no matter what we do, it's a bit of bad luck, right? If there is a fault happening in the middle of your house, it doesn't really matter how strong your house is, you're going to probably have a bad time. But flexure damage and shear damage are things that we can easily control. This is a dictionary, a visual dictionary of typical damages that happen in unreinforced masonry buildings after earthquakes. And I included this just to remind ourselves that the alternative is not great, right? Unreinforced masonry does not perform very well in earthquake zones, and that's why we went to this concrete systems. There's a good rationale for it. And the concrete system is quite flexible. Moment frames are notoriously flexible, so that's a really good thing for earthquakes. And they also use less concrete than like a concrete shear wall system, which also is a lot more economical. I'm going to go a little bit faster over this because we had a brief introduction about that earlier. But planning is obviously a key first step to make things better. It's not just about construction accuracy. We can make buildings that are better by having them be simpler in plan, be more coherent in elevation, and more consistent as the lateral system goes. The code will really guide the design professionals to do a better job, and in some areas will restrict or prevent some of these systems to work. So we saw how these columns are typically the weakest link, and I think that's maybe the biggest lesson to walk away from with this lecture with. When the building is moving and we have a moment frame system, these columns tend to work the hardest, And there's more and more load as you go towards the ground, because that load adds as you go down. And so the columns at the base of your building are working the hardest. And that's the typical failure mode, where your columns fail. This is here a relatively lucky picture where you can see that the energy of the earthquake was dissipated very locally. The concrete exploded out, but luckily enough, there was enough reinforcement to keep the building standing. And that's really one of the key takeaways here, is that a lot of earthquake design is not about the building being undamaged, but allowing you to leave the building safely, right? And we'll maybe discuss that during the questions later. This is another column jacking example from Studio Nyandak in town, where the columns are being reinforced. And that can be done easily with a sleeve and additional reinforcement. Ultimately, when it comes to reinforced concrete, it's not a very glamorous exercise to make your structures safer. And it really comes down to very, very small, minute detail, which may not look very important, but really make a difference. And it's a lot has to do with rebar placement and having the right overlap between your bars, or the right amount of bars, or the right spacing between your bars. And there's a lot of rules as to how one should do that. I'm probably not going to go too deep into this, but here you see some diagrams that illustrate what appropriate reinforcement strategies would be for beams. We would want stirrups, which are shear reinforcement, to be much more tight towards the columns. It's a lot about this joint between the column and the beam. And then similarly, we want our columns to be very strong with tighter stirrups towards the joints. We want bars to be anchored properly, and that's also especially difficult to achieve at boundary conditions where your beams are not continuous. At the foundation, this could also be an issue where your columns could come out of the ground or punch through your footings. And so similarly here, the code will guide you and recommend the right amount of reinforcement and the right details. And this is a really challenging aspect of the job, is to convince contractors who've been working for many, many years and have done things the way they've done them for a long time, that this could be valuable when for them it represents an extra cost and is not always an immediate benefit that's visible to them. On site, we can have other issues with concrete, just the quality of the materials. We talked about contractors not using enough cement in their concrete mixes. Pouring concrete can be really difficult or really messy. So you could have voids in your concrete if you don't vibrate properly. There's a number of issues that could happen. Curing, which is how you bake your cake, is obviously a very important aspect of baking. If you bake your cake too much, it's not going to be very good. The same thing happens with your curing process. If it cures too fast, your concrete will crack and will not perform very well. So all of these things are aspects that can be trained with contractors. And I think the last thing I'll talk about before we open it for questions is going to be this balance between a design criteria, which is an objective of how we want our buildings to perform, and then how much resources we have in time and money. And that's always the heart of the problem. The code will have very specific guidelines for what a hospital should do. And we want hospitals to be fully functioning after an earthquake, because those are areas where we're going to have a lot of needs for resources. People will want to go there. But for houses or most buildings, this is not necessarily required. And that's a fine balance to find between spending a lot of money to make a building resilient and then make a building that's just good enough for you to be safe when an earthquake happens, which could be a lot cheaper. So that's a tough thing to argue and a tough thing to really calibrate properly. Ultimately, we all want to be safe, but none of us really want to spend too much money to retrofit our homes.
we'll open up for a 20-minute question and answer session with our three speakers. If you raise your hand, we'll bring around a mic to you.
Yumso.
Hello, I want to say thank you for your presentations. I have a few questions. Your assessment at TCV, are you going to retrofit the areas that are, the buildings that are not safe or need to be made safer? Is that in your plans? The buildings that are like, that were red in your diagrams?
Thank you for your question. So as you saw in the presentation, there was about, I think, 40 building blocks that we the assessment on. Now, out of which all of the building blocks had different risk levels, right? Right. And based on the human hours that we did initially, we were better able to prioritize the building based on the vulnerability ranking, right? So we are planning on retrofitting, but in order to retrofit, we wanted to do our own shock table simulations so that we are better able to retrofit with our own strategies. Because if you saw in one of the slides, you saw a photo from Nepal, the UN, by UNDP, which was containment reinforcement. So as I said, TCV has a lot of different construction topologies, from reinforcement concrete to unreinforced masonry load-bearing walls, right? So different strategies need to be implemented depending on the structure. So we are planning on doing retrofitting, but that depends on the type of structure, and we have to come up with own strategies depending on the region and the building type.
Also, is there an earthquake preparedness plan for Dharamsala? So you were mentioning that there are plans for emergency response, but to my knowledge, there really isn't much information for the normal person who lives here on what to do in an earthquake and how to be prepared. Is there information out there for that?
That is very true, because in terms of planning, I haven't seen, or maybe I haven't done enough research, but I haven't seen just of yet at the planning strategies for in terms of an earthquake.
We do drills, earthquake drills in schools. So one of the major, how do you say it? In my presentation, I have this section where I talk about the crucial infrastructures. So the places of gathering where there is lots of people and lots of people living under a same roof or being under one building is more vulnerable when it comes to like the number of casualties, right? So that's why when I was in TCB, I did had the earthquake drills, and I also think that, and I've also seen that the Himachal government, they have been doing earthquake drills in specifically in schools. And in my knowledge, I haven't seen any earthquake drills in hospitals or around like areas like institutions, or I'm not sure about library, but yes, it is recommended. It must be done, the preparedness drill, when it comes to large community. But in terms of your case, or it can even be me when I live in a house alone, then there is this one or two exit that, and it can be only one or two people living in that house. So it's easy to exit. But when it comes to large community, it's hard to exit a whole lot of population, you know, like in the right direction. So that's why it's important to, you know, have an earthquake drill in larger community and or like places of gatherings. Yeah.
Okay, thanks.
Hi, my name is Prabhu and I work here in Dharamsala. Thanks all for this wonderful presentation. My question is to you, ma'am. So, great presentation, just the fundamentals, a little technical. When you were talking about the magnitude of the earthquakes, it's assumed to be the Richter scale. What other seismic metrics can you elaborate on? And also, there's the Himalayan Institute of Geology, I think, in Waupun and Dal Lake. Do you think of collaborating with them in some?
Yeah, first of all, the National Seismology Center in the Nadi, we did try to reach them, but we did not get any proper a connection. So we are planning to do that more and get involved with the connections with them. Of course, because it's a big national center, so our research project does need their help and information. And regarding the scale, the magnitude here I have used is of the Richard scale, right? And we do have other scales as well, and there are some other ways to classify or how do you say it? Scale the magnitude, right? But here in this presentation, I have used the Richard scale only. Yeah, thank you.
Hi, my name is Vikram and my question is for Paul. I wanted to ask you, as you've already mentioned, that the soil here in Dharamshala is not that hard. So when an earthquake hits, the probability of the building falling down is a bit more higher. What can be done in that regards, and are there new technologies coming up for these kind of soils all across the world or not? Thank you.
Thank you for your question. I think when it comes to soil stabilization, this is a very challenging topic because usually the measures are very costly. But one strategy that probably is most appropriate is to have deeper foundations because these will help resist sliding, which is another big issue.
No, but the stones are also very soft here.
The stones are very soft?
That is what she mentioned, right?
But if you go with deeper foundations, it will help you no matter what, right? Even with liquefaction, where the soil, with the shaking of the ground, the clay might become liquid temporarily, which is a very striking event where your building essentially sinks into the ground or tips over. But your deep foundations will help you stabilize and mitigate that problem. But that would require having piles and drilling into the ground, which, is not something very straightforward to do.
I would like to add one thing on that, is that we here in Dharamsala area, we tend to give our new constructions to contractors, and we do not tend to do soil investigation, soil investigation. So I think that is the big plays the biggest role when it comes to building a new construction. So the soil investigation tells us how deep can we go to get the hard rock and stable soil, which can encounter the building load that you are planning to build, right? According to how large the building is, how much load it can, it is servicing, then according to that, you can build and get the depth you want. So in that terms, you can also, have a good base. Yeah, I would say.
Hello, my question is to Paul. I want to ask, how to use base isolator and how to cast concrete upon it.
Thanks for your question. You would place your foundations the way you have always, but instead of having your concrete columns coming out of your foundation system, there will be a joint, and the bottom foundation and the bottom of the top of the foundation and the bottom of the column will interface a system. There's lots of different options out there. Typically, there'll be steel rollers, so two pieces of steel that are able to rock on top of one another. It's a little tricky because obviously there's a lot of load, so whatever system you have in place needs to have that capacity to transfer that load, but allow the movement. This typically will happen through a steel plate, or it will be a stack of rubber joints, and instead of having a real sliding effect, you'll just have a local rocking that will be controlled through the hardware that you provide very locally and that is specifically designed for that load.
Yeah, I just wanted to add to you. So base isolation, it's very technical. It's a very high-tech technology, requires a lot of expertise, and you need to source the base isolators also. So it's very expensive. It's very hard to use in a low-cost setting. I've seen some research done in Iran where they try to develop a base isolation system for low-cost use, but the problem, and they use like a gravel instead of a base isolator. But the problem is with base isolation, you need to bring the building back to its original location. So with gravels, that's a challenge. And then to add to your point, the previous question, as Dechen mentioned, if you do the soil testing, you will know the soil bearing capacity at each depth, because the soil testing will do like a SPT test, and you'll know like if you go down 2 meters, you'll get this much bearing capacity. If you go 5 meters down, then you get higher bearing pressure.
I think my question is mainly for Paul. It's two questions. So about, it's related to what he said about the soil. We tend to build on slopes here. So most of your illustrations were about flat ground, right? And which means that you're just cutting into the slope and then you're putting it in the ground. So what happens if you're trying to avoid that? And if you have a slope, is it better to have a stepped sort of construction, or if you end up then flattening the mountain and when it's a larger area? So you build, how tall can you build? So which of the scenarios is safer?
That's a very good question. I'm afraid the answer is not the one you want to hear, but the safer approach would be to excavate the mountain deep enough that your building has the same ground and you can build it up from that elevation, and it becomes a very standard building with as tall as you need it to be. The challenge with having stepped buildings, which are much more affordable and perform much better in all other ways, is that you get energy input at each level, and that will really create challenges with your lateral system and the structural integrity of the system. One approach would be to have individual independent buildings, and you could introduce seismic joints, and so each step is its own little building, and that way you avoid the problem of having split levels or irregularities, which the code will advise you against.
So it's like having an expansion joint, but
Correct.
Kind of like that.
Yeah, exactly.
But
like that.
then does the fact that you have, like say if you can have 2-story stepped structures instead of having a 10-story high-rise structure, does that make a difference?
Does that make a difference?
Yeah.
I mean, it would be a lot cheaper to build, for sure, yeah.
But seismically, I mean.
Seismically, the taller building that is straight and has a consistent lateral system will perform better.
We have time for 1 or 2 more questions if there are any more.
So for a layman like me, this was the discourse was like listening to emptiness. Joking. So I was really wondering. I mean, I think it's there. We need to really have a easy to practice manual of a pamphlet of this size, where ordinary people can really take care and do small things for this earthquake risk or hazard preparedness, and then distribute it. And I'll be happy to publish such a pamphlet if you give me the contents.
I think from a design standpoint, it's a very realistic goal to have a couple of to-go designs, and people could pick, from 5 options for 5 different kinds of houses. These are designed a bit in a vacuum. They would still be earthquake resilient, and I think a big improvement from a potential improvised design by a good intention contractor. So that could be something that helps. But I think when it comes to preparedness at a bigger scale, it's a lot more than buildings when it comes to earthquakes. I think a lot could be done, but maybe you guys can comment.
Well, I'm not even talking about the building for the time being.
Yeah.
Because I'm having a clear picture of Megalopad, the buildings, built one upon another, ready to come down.
Yeah.
So at least, the building part, because of shortage of funding and other things, they will not be able to do, but at least, preventing fire hazard and objects falling from here and there, whatever, all those things.
Yeah, we've thought about it, and I think that's a great idea. We'll work on a pamphlet. One for with Paul Log, we can make one like a design guideline, and then another pamphlet for earthquake preparedness, and what are the non-structural things that you can do? What are the changes you can do in existing building? If there's an event of earthquake, which corner of which part of the room is safer? Which parts to avoid? Yeah, we can work on it. Yeah.
Thank you for your presentations. Most of us here, I don't think we'll be building big constructions and big houses. So our main concern is what you have just discussed previously, the probability of an earthquake around Dharamsala. Because this will affect every one of us, but we will hardly build houses or buildings or hotels. Maybe few, the leaders of the institution, they should be here to hear your lectures. But our main concern, I think, is the probability of the next big earthquake.
Yeah, I discussed about that in my slide, the probability of recurrence of earthquake similar to the 1905 Kangra earthquake. I'm not sure whether you were present when I was giving the last slide, but let me repeat it. So according to the geologists and experts who have been studying and have been doing research on the probability, there had been two conclusions or estimations that they have given, and overall it have estimated, or the probability have been come to within the 50 to 100 years, there is the probability of major earthquake. We are not talking about earthquakes less than 5 or 6. We are talking about big earthquake that is more than 7, and it can even go further over 8, because there had been no there is no exact research which can tell exactly what happened during the 1905 Kangra earthquake. So I have been doing many research and have been reading lots of articles that the geologists and experts have been published. So according to them, there had been no solid research which shows at which point and from where it occurred and how big it could have, the 1905 Kangra earthquake, it could not have been the largest or the major earthquake that happened. It might date back before the 1905. There might have been more magnitude of more than 7.8 earthquake, and we don't have any records. So that's, I think, a point to keep in mind. Yeah.
Can I add a little bit on that? So the point of our presentation is we might not be building a new building, but we are still living on the building, right? And we need to have understanding we need to have the understanding of in what kind of building we are living in case earthquake hits. That's why this presentation.
Yes, thank you for your presentations. I'm impressed by all the knowledge you have acquired and made systematic, and all these interesting and important advices on actually how to build, to avoid, and also to improve the existing buildings. But I wonder, could something be done on a regulative basis by the municipality, that you could get it into the building regulations, that in order to build a new building here, you have to have those and those rules, and retrofitting, then these things has to be done. And maybe also on another level, there should be advices on sites you are not allowed to build on.
Thank you for your question, Ingrid. So no, that's very true. I completely agree with what you just said. And in one of the slides I covered, so policy integration that I talked about, which I feel is very important, because most of the constructions that's being done right now are engineered to some extent, but what matters, what's important is that the work that's being done is not being inspected properly or doesn't follow standard codes. So all of the drawings, whether it be technical, the rebar detailing or any technical drawing, it's not been verified all the way, and so it's not, there are no special inspections. Like the work we do with New York, there are special inspections where each building structural elements have to be specially inspected by a technical person who knows the art or the design. So that kind of system is not implemented in Dharamsala. And as you saw, Taru, the consultancy, they worked with the Himachal State Disaster Management. So that forms sort of, I mean, I think that is one of the first steps that Himachal Pradesh has moved in terms of safe, I mean, seismic safe buildings. But yeah, I would like if the Himachal State or the Indian state, I mean, the nation, could do further on what you just said.
I think that's all the time we have now for questions. We're going to take a short 15-minute tea break outside of the library and then meet back around 4.